We are looking at three-phase power calculations, and in this example here we are going to be calculating the total power of a three-phase circuit with multiple three-phase balanced loads. So let's have a look at what we're talking about. So in this case we've got a 347 600 volt supply, three-phase 4-wire. On this we have got a lighting panel that draws 98 amps, 0.75 power factor. We've got a 40 horsepower motor with an efficiency of 80%, and it operates at a 0.85 power factor. Plus we've got three 100 microfarad capacitors Y connected, all on our same circuit here. So what we're going to have to do with this is we are going to have to construct power triangles for each one of these, or determine each one of them is apparent power, true power, and quadrative power. And then we are going to add up all the true power, add up all the quadrative power to get a total quadrative power, and from the total true power and total quadrative power we can get our total apparent power of the circuit. So let's go ahead, and I've given you a couple of examples here of different types of loads, or how you might be given the information. So I'm going to go through each one of these loads and construct the triangle one at a time. So if we begin here, I'm going to start on our lighting panel. So for our lighting panel, we can go ahead and calculate the apparent power of the lighting panel. So I'm just going to write that down. S of the lighting panel is going to be equal to our three-phase formula, V line times I line times root 3. So that would be 600 volt times 98 times root 3, and that should come to about 101,845. Alright, and so that's our hypotenuse here on this triangle. So S of the lighting panel is going to be 101,845 VA. So from there we can go ahead and calculate the true power of the lighting panel, so PLT. So we can use the same apparent power and then just multiply it by the power factor. So just keep in mind, power factor is the same as the cosine of whatever phase angle the circuit's at. So if I take 101,845 VA, times that by a power factor of 0.75, that's going to come to about 76,300 watts. So that's our horizontal power of the lighting panel, 76,383 watts. Okay, so for the quadrative power, I can go ahead, a couple ways to do this while we're looking at it. It's a 0.75 power factor, and if I take the inverse of the cos of that, so second function cos of 0.75, it's going to work out to about 41.4 degrees. So a couple methods that we could use to figure out our quadrative power of our lighting panel is, one, we could use the same thing. We could take the apparent power, three-phase apparent power, and times it by sine of angle theta. Or if you look, we have simply a triangle, so we could also go with square root of the S total squared minus the power total squared. Either method that you use, it's going to work out to about 67,365 var. So Q of the lighting is going to be 67,365 var. Okay, so we've got all the values of the lighting panel. Let's go ahead and look at the motor now. So I'm just going to talk briefly about the motor. When we're looking at the horsepower of a motor, what that refers to is the power output of the shaft, the mechanical work that it's doing. Okay, so the rate at which it's doing work mechanically. And when we look at the next value given here, it's the efficiency. So efficiency means that 80% of what electrical input I have to put in, I only get the 40 horsepower out. And what we're concerned with is the total true power that we have to put in to that motor to make it output 40 horsepower, as they have losses. Sometimes values, the FLA, will be given. From there you could use your three-phase formula and figure it out just like we did with the lighting panel. Other times you might be given just the horsepower and the efficiency and the power factor, and we have to figure it out from there, as in this example. So if you recall 40 horsepower, every 1 horsepower for the conversion, it's 746 watts per horsepower. So I'm going to go ahead and calculate the power output in watts of our motor. So power output, and that would be equal to our horsepower, 40 horsepower, times 746 watts per horsepower. So our horsepower output in watts will be 29,840. All right, now I can sub that into our efficiency formula and just kind of work it backwards. I'm just going to recall that. So that would be power output, simplest version, over power input. And what I'm looking for is the power input. That's what's going to go on our power triangle. So I'm going to take my power output and I'm going to divide it by my percent efficiency. So that will come to approximately 37,300 watts. So I take 29,840 watts and divide it by 0.8%. So, okay, now that we go at our power input, I'm going to label that here. So that's our power, true power of the motor. So 37300 watts. And I know that this power factor of this motor is 0.85, so I can put that on my triangle. If I want, I can convert that over. So second function cosine. That's going to come to about 31.79 degrees. So from here, I'm going to go and calculate the apparent power of the motor. So remember, the power factor is the ratio of true power divided by apparent power, so P over S. So if I want to solve for S of the motor, I'm going to take my power of my motor and I'm going to divide it by my power factor. So I'll take my 37,300 watts and I'm going to divide it by 0.85. And that will come to about 43,882. Put that on my triangle, 43,882 VA. Next thing, quadrant power of the motor. Once again, we've got two sides of a triangle. So you could use our formula there with apparent power times sine theta, so that how they write it out in your book, V line times I line times root 3 times sine theta. This will work. Or you could use Pythagorean theorem again. So you take your S of your motor squared minus the horizontal, so P of the motor squared. And either way you do this, you should get approximately 23,118 var. So I'm just going to go ahead and put that on my triangle. Q of the motor is 23,118 var. So we got all three values of our power triangle for our motor. Let's go ahead and work on our capacitor here. So I'm going to take a little bit of a longer process on this one, just right from the beginning. There is shortcuts you can take, and when we get to power factor correction, that's when we'll explore those options, those shortcuts a little bit more. So in this case, we've got three 100 microfarad capacitors connected up in Y. So this is a 60 hertz circuit, so 60 hertz. We are going to go ahead and convert that over to its reactance at 60 hertz, so each one of them. So XC is 1 over 2 pi FC. And if we sub that in, we should get around 26.53 ohms. Okay. And the next thing we can do is, well, we calculate phase current. And just recall, this is a Y-connected load, so that would mean that the line is the same as the phase. So if I take my voltage of my phase, and I divide it by my XC in each phase, I should get my line current. So the phase voltage will be 347 volts, divided by my XC of 26.53 ohms. And the current in the phase is about 13.08 amps. Okay. All right, so now I can figure out the total apparent power. And in this circuit, or the apparent power of the capacitor bank, in this circuit, we know the property of a capacitor. Current is going to lag voltage by a full 90. So there is no true power at all in a capacitor bank. It is all wattless power or quadrative power. So in this case, the Q total, QC total, is the same as the SC total for that capacitor bank. So we could go ahead and use our apparent power formula for it, V line times I line times root 3, and we could times it by sine theta. Well, sine of theta, that's 90 degrees. If you type in sine 90, that is just 1. So the apparent power is the total reactive power of the circuit. So when you do this, it'll come to, well, let's go ahead and figure it out. 600 volt times 13.08 times root 3, and that will come to 13,593. So I'm going to go ahead and put that on my line for my capacitor. So 13,593 var. So we're done each individual load, breaking it down into its horizontal and vertical components. So now it's just a matter of adding up our horizontals and our verticals. So we'll add our P's. So if I add the power of the lighting panel to the power of the motor, and there's no horizontal at all in the capacitor bank, I'm going to get a total true power of this circuit equal to 113,683. All right. And if I add up all the verticals, so when we do this, we can go QLT. So if we call this a negative, you can do it that way. So what you want to do is keep in mind that we would add the negatives here and then subtract off the positive value or the opposite value. Okay. So I guess we could do it this way too. We can say that the Q total, where should I put that here? Q total, we could say it would be equal to the Q of the lighting panel, and it's going to be a negative, plus the Q of the motor, and it's also a negative, plus the Q of the capacitor bank, and it's going to be a positive value. So in this case, I've pre-drawn my total triangle, so I know that it's going to still be lagging in the end. So we're going to go ahead. Another way to shortcut to do it is we add these two negatives and then just subtract off the QXC. We need the net value. So the Q total, we go ahead and add that up. So 67,365 plus 23,118. Subtract 13,593. I know that it's going to leave me with a net of 76,890. So now that I've got my VARs and my total true power, I can go ahead and calculate my S total of the circuit. Okay, so for the S total, I'm going to use Pythagorean theorem. I've got my adjacent and my vertical, so I'm going to take my P total squared plus my Q total squared and square root the whole thing. And my S total will come to 137, 244 VA. So that's the total apparent power. So what else we could calculate is the power factor, the total power factor of the circuit. And if I want the power factor of the circuit, I have to take the P total and divide it by the S total. So in this case, we've got 113,683 divided by 137,244. And in this circuit, it should come out to about 0.828 for a power factor. Now, what if the question asked, what's the total current of the circuit? Well, if I know the total apparent power, I could use my three-phase power formula and just transpose it. So S total equals V line times I line times root 3. So if I want to solve for I line, I'm going to take S total and divide it by V line times root 3 in brackets. So if I've got 137,244 VA, I'm going to divide that by bracket 600 volt times root 3 in bracket. And this circuit, we could expect to see a current of about 132 amps approximately. Okay. All right. That's a lot of work, but hopefully that helps you out. And we'll see you on the next video.